Hello, fellas. We are a group of Chinese students from different universities who are more than happy and privileged to present our project to you. Our project is about building up a drift diffusion model in working memory.
The information in working memory is not stored with perfect fidelity. It changes over time. In the experiment, subjects needed to remember the color of 1, 2, 3 simultaneously presented stimuli. After a short delay, they should report their memory of the color at the cued target location, using a continuous scale. Results showed that their reports had evident clusters, though target colors distributed uniformly. So the questions are, how do the clusters emerge? What's the temporal evolution process of the visual working memory? Here we go to answer them.
In order to answer this question, we developed an attractor model, which means there exist some attractors on the color space in our memory. For a given color in our memory, it will be attracted towards their attractors. At the same time, this color also experiences a random diffusion process. So we can see here, the time evolution of a color in memory is influenced by a deterministic part, as well as the white noise process. And actually, we spent a long time on understanding this attractor model with drift and diffusion part and how to implement it in MATLAB. First, we need to describe their drift function. We used the weighted sum of 12 basis functions to obtain their g theta, and then we rewrote the equation 1 in a Fokker-Planck equation form. After discretization, the change of p theta t over a given time point dt can be described by the Markov transition matrix, and then we could obtain their p theta t from their p theta 0. This is the data set we used, 200 sample trials data with information of delay time, report color, and target color. And now we have their model and we have the data, and we conducted their parameter estimation process with maximum likelihood estimation. Now we got all the parameters we need. Let's look at how they work.
After parameters estimation, we simulated the results from target to report with such a drift diffusion model we have mentioned before. The upper left figure shows that both the simulated report and the true report exist several clusters rather than uniform distribution like the target. Then we simulated the memory trajectories and showed it in the bottom left. At the beginning, the color in memory is uniformly distributed. Although there exists diffusion noise in the whole time course, the memory of color drifted to the attractors in the process of time. Their 4 attractors correspond to the 4 attractors in the upper figure. Therefore, the drift diffusion model can simulate the phenomenon that attractor dynamics influence memory presentations.
So we also simulated the drift function of g theta. As we can see from the top right, we plot the drift function and marked dots where equation is equal to 0. Based on what we have learned in the tutorial of the second day of the third week, the dots are fixed points. However, their stability is not the same. In this case, the green dots represent stable fixed points that are defined as attractors. The red dots represent unstable fixed points, which tend to cluster towards lateral attractors. The plot in the bottom right simulates possible trajectory of a stable and unstable fixed point. You can see the memory of an unstable point would be drafted to lateral attractor over time.
So, to summarize, there are 2 forces driving the evolution of visual representation in a working memory process. First, a random diffusion, and second, a drift towards discrete attractor states. In the future, if it is possible, we would love to expand this into a Y model, which means we want to see if there are some neural foundations or biological constraints that lead to the existence of such attractors. And last, I would love to express our deep appreciation to our mentor, Alex, and our TA, Chenli, for the help on our project. And also, our great thanks to all the hardworking NeuroMatch staffs for doing everything. Thank you.